talk about measurements, measurement devices, and measurement uncertainty for this lab that you're doing this week. Okay, so our standard measurement device in this physics lab for this semester is going to be our meter stick. Okay, so at the SI fundamental unit of length is 1 meter. That's this thing right here. 1 meter is 100 centimeters. So on a meter stick, we have 100 centimeters marked out on here. Okay, and every measurement device has an uncertainty built into it. Usually that uncertainty corresponds with the smallest demarcation that you see on that measurement device. So the smallest demarcation that we have here is at 0.1 centimeters. So the uncertainty on any measurement we take with 1 meter stick is going to be 0.1 centimeters. Okay. So if I, for instance, here I have a zucchini. I've been doing a lot of gardening this summer, so I have my zucchini, and I want to take the measurement of the length of this zucchini. So if I place it here on my meter stick at the end, that's approximately at the end right here, I think that the length of this zucchini is something like, let's say that that's 23.6 centimeters. It's a little bit hard to tell because of this sort of, the fact that the zucchinis aren't perfectly flat on the end. So let's say 23.6 centimeters, and I would report that measurement as 23.6 centimeters plus or minus 0.1 centimeter, because 0.1 centimeters is the uncertainty that accompanies a meter stick. Okay, now every device has an uncertainty on it. Now we've got our meter stick here, but a caliper, which is a device that helps us measure smaller objects more precisely, or smaller distances more precisely, the uncertainty on a caliper is 0.01 millimeters. So there's 1,000 millimeters in a meter, and this little caliper here measures to an uncertainty of 0.01 millimeters. That means that every time you take a measurement with a caliper, you know your measurement within some degree of certainty to 0.01 millimeters. That's pretty precise for that measurement, okay? So those are for lengths, these devices here. You might not get to calipers this semester, but we'll use it a little bit if you're with me next semester in physics. Hopefully we'll be in lab by then, all of us together. Now, what if we're taking measurements of time? Measurements of time with a stopwatch. So you could use a stopwatch if you have one, or you could use a clock or a watch, or you can use the app on your phone, the stopwatch app on your phone. Now, the thing with time measurements, if we're taking them as the human, is that measurement has to incorporate our human reaction time. And our human reaction time is 0.25 seconds for a visual cue. So anytime I see something happen, it takes my brain 0.25 seconds to register that it saw something happening and to make a reaction. Okay, so let's say that I'm watching someone run a race, and I want to see how long it takes them to run that race with my stopwatch. So I have to click start when they start their race, okay? That takes me 0.25 seconds to see that they've started the race and to press the button here. And then when I see them cross the finish line, it takes my brain another 2.5 seconds and my body to react to that, okay? So altogether, that's 0.5 seconds if I'm using my human reaction time to record an event from start to finish. So if I'm taking a measurement of something with a timer that incorporates having to take a time, and I, as the human, am taking that measurement, I'm going to record an uncertainty of about 0.5 seconds on that measurement. Now, a lot of the things that we're going to do in this class occur very quickly. If I want to say, for instance, measure the time it takes for an object to drop a short distance, let's say from here to here, that time for it to drop is maybe 1 second, maybe even a little bit less. And my human reaction time being 0.5 seconds for that entire duration is really close to the length of that fall itself. So we really have to think about these uncertainties so that we can think about how accurately do we know our measurement, how well do we know that measurement to some degree. of certainty. Okay, so that's something that we're going to take into account and we're going to think about this semester. Now, we are going to do a little activity for the first part of your lab. We are going to do an activity for the first part of your lab that might seem a little bit silly, but I think it's kind of fun. Now, we are going to measure the length of a door for this first activity, the height of a door. Now, I know that not all of you are going to have some ruler or yardstick or measurement device like this at home. So I'm going to show you what we're going to do as a fun way to measure the height of the doors in our houses. I can measure the height of the door in our lab right here using my meter stick. And if I do that, I see that the height of my door is 100 centimeters or 1 meter plus 200 centimeters, 2 meters plus, let's say that's about 13 centimeters there. So 213 centimeters is the height of my door, or 2.13 meters, because there's 100 centimeters in a meter. And I would report, maybe I would report plus or minus 0.1 centimeters on that measurement. If I'm saying 213 centimeters plus or minus 0.1 centimeter. But you saw that I had to replace that meter stick 3 times when I took that measurement. That's going to affect the certainty, or the uncertainty on my measurement. Is going to bump up that uncertainty, okay? And also, you know, at the end there, maybe I didn't get such a good measurement because the door is much, much taller than I am, okay? So if I were to actually report that measurement, maybe instead of saying 213 plus or minus 0.1 centimeter, I might say 213 plus or minus 0.2 or 0.3 centimeters, just to incorporate the fact that I had to, you know, replace that meter stick a couple of times. Now, if I had a continuous meter stick that went all the way to the roof, I could report just an uncertainty of 0.1 centimeters on that measurement, since I wouldn't have to replace my measurement device over and over again. Now, in your lab kit, which I hope to give you all in the 2nd or 3rd week of lab when you come in for your face-to-face lab sessions, you will have a meter stick, kind of a meter stick that looks like this. It's actually 1.5 meters long. This is what you can use to take measurements. The top side of it is going to be listed in units of centimeters. The bottom side is going to be listed in units of inches. We don't want to deal with the units of inches here. We're going to deal with the units of centimeters for this class. We're going to stick with standard SI units for physics. And also the uncertainty on this little measurement device is going to be 0.1 centimeters, because that's the smallest demarcation on this ruler here. Okay. So one way we can think about uncertainty on our measurements is by calculating something called the percent uncertainty. So here is the equation for our percent uncertainty. The percent uncertainty is equal to delta A over A times 100%. Okay, so delta A, this little symbol here is supposed to be my Greek lowercase letter delta. Delta A is the uncertainty on a set of measurements. Okay, rather than the uncertainty on one measurement, this is the uncertainty on a set of measurements, many trials. Okay, and then A is my standard measurement, maybe what someone suggests that this measurement should be, or it could also be maybe the average of all of my measurements too. Okay, there are a couple of different ways you could think about it. But let's think about a particular problem here. Let's say that over the course of the summer, I've been buying 5-pound bags of avocados. I love avocados, one of my favorite things. So the store says my bag of avocados that I'm buying every week should be 5 pounds. But over the course of the summer, I actually took those bags and I weighed them to see were they actually 5 pounds or not. And doing that, I can get an uncertainty on what this 5-pound bag of avocados is. So the first bag I measured to be 4.8 pounds, the second to be 5.3 pounds, the third to be 4.9 pounds, and the fourth to be 5.4 pounds. Now to get this delta A, this uncertainty on the set of measurements, what I'm going to do is I'm going to go through all these measurements and see how far are they off from what is suggested the weight of this bag should be, 5 pounds. So this first bag is 0.2 pounds off. second bag is 0.3 pounds off. My third bag is 0.1 pounds off. And my fourth bag is 0.4 pounds off. Okay, so what I'm going to do for my value of delta A, I'm going to look at how far each of these measurements were off from the suggested value. And I see that my fourth measurement here has the largest uncertainty, the largest excursion from that was suggested to be that 5-pound bag. And so I'm going to choose for my delta A here, this quantity, the 0.4 pounds. This is the largest uncertainty on any one of my 4 bag measurements, okay? Because some of these others are much, much closer to the measurement, but I found that, in fact, I could be off from that 5 pounds by as much as 0.4 pounds. And so I'm going to use this largest excursion from the suggested 5 pounds as my uncertainty here on my set of measurements. So we want to be as clear and honest as we can when we take our measurements and report our measurements. And so if we have a measurement that has a very large uncertainty, but maybe some of them are a little bit smaller, we still have to take into account that measurement that had that large uncertainty too. Okay, and so that's what I'm going to do here. I'm going to go with this largest uncertainty that was on one measurement for one particular bag of avocados and use that as my delta A here. Okay, so then if I do that, then my percent uncertainty becomes 0.4 pounds, because that's what I'm going to use for my delta A, divided by what was suggested for that standard weight of the bag should be, which was 5 pounds, and then multiply that by 100%. Okay, so we see here we've got pounds over pounds, those units cancel, and so I have 0.4 divided by 5, and multiply that by 100, and that gives me 8%. So I see that I actually have 8% uncertainty on the measurement of these, what are supposed to be 5-pound bags of avocados. Okay. One more thing, if I asked you to formally report that measurement with the uncertainty, this is how you would do it. You would say, I'm going to say 5.0 pounds plus or minus 0.4 pounds, okay? And we found that that was also 5.0 pounds plus or minus 8%, okay? So this tells us that my bag of avocados could weigh as much as 5.4 pounds, that's 5 plus 0.4, or as little as 4.6 pounds, okay? So that's the 5 minus 0.4 here. So my bags of avocados could weigh anywhere between 4.6 pounds and 5.4 pounds and still fall within this 8% uncertainty on the measurement.